everybody. Today we're going to be going over chapter 5, and that's arrays and the elements of programming interviews in Python book. Um, so I always like reading the quote just because it's pretty inspirational. Alan Turing is, I don't want to say obviously, but a huge inspiration to me, and I think for a lot of other programmers. If you haven't watched the movie Immersion Game, I think it's called Immersion Game, Imitation Game. Imitation. Yeah, Imitation Game. I'd highly recommend it just because it's really, really, really good. So the quote is, "The machine can alter the scan symbol and its behavior." Um, okay, the machine can alter the scan symbol and its behavior is in part determined. Okay, let me say that again. The machine can alter the scan symbol and its behavior is in part determined. Okay, I would assume this quote actually is supposed to say, the machine can alter the scan symbol and its behavior, or the ability for a machine to alter its scan symbol and its behavior is in part determined by that symbol, but the symbols on the tape elsewhere do not affect the behavior of the machine. I would assume this is something to do with comprehension, right? It's not just, it's a machine that just chugs out information or garbage or data or whatever you want to look at it. If you just give it something, it's sentient or as close to it as possible, in that you feed it information and it gives you something useful. Profound, as always. Uh, okay, all right. Um, the simplest data structure is the array, which is a contiguous block of memory. It is usually used to represent sequences. Given an array, um, one second. What was that? No, I don't want this to go away. Okay. That's what I wanted. Okay. It is usually used to represent sequences given in an array A. A of I denotes the I plus 1th object stored in the array. Retrieving and updating A of I takes O of 1 time. Insertion into a full array can be handled by resizing. Um, Allocating a new array with additional memory and copying over the entries from the original array. This increases the worst case time of insertion, but if the new array has, for example, a constant factor larger than the original array, the average time for insertion is constant since resizing is infrequent. Deleting an element from an array entails moving all successive elements one over to the left to fill the vacated space. Right, that makes sense. So you have an array and you're deleting an element in the center, you'd have to move everything else over. For example, if the array is 2, 3, 5, 7, 9, 11, 13, 17, then deleting the element at index 4, which would be 9, results in the array 2, 3, 5, 7, 11, 13, 17, 0. 0, right? We do not care about the last value. Okay, apparently. The time complexity to delete the element at index I from an array of length is big O of n minus I. The same is true for inserting a new element as opposed to updating an existing entry, which makes sense if you're going through the array from the first element onwards and eventually delete an element. So that's why it's big O of n minus 1. If you're not familiar with big O notation, I'd highly recommend looking about it, reading about it. I think the book has a chapter about it, so please check that out. So Array Bootcamp. All right. The following problem gives good insight into working with arrays. Yeah. Your input is an array of integers, and you have to reorder its entries so that the even entries appear first, right? So let's say we have an array. That's gonna be 1, 2, 3, 4, 5. So you'd want an array, uh, even array, that given A would turn it into 2, 4, 2, 4, 1, 1, 3, 5. right? Right. So what, let me just reformat this. Okay, never mind. Can okay, all right, cool. Just hate those warnings. Okay. Yeah, okay, cool. So we do not care about the last value, the time complexity to delete. Okay, that's not where I was. Yeah. Yeah, the following problem gives good insight into working with arrays. Your input is an array of integers, and you have to reorder its entries so that the even integers appear first. This is easy if you use big O n space, where n is the length of the array. However, you are required to solve it without allocating additional storage. All right, yeah, that's true. Right. So if you were to use extra arrays, that's pretty straightforward. That's literally what I have over here. But if you were to do it in place, um, meaning your space complexity would be big O of 1 because there's no extra space, um, then it would be a little harder, right? So when working with arrays, you should take advantage of the fact that you can operate efficiently on both ends, right? So this is the idea of pointers, not really memory pointers, but pointers, in that you can work not just with just the iterating variable, or not just with one iterating variable, you can work with many. For this problem, we can partition the array into three subarrays: even, unclassified, and odd, appearing in that order. Initially, even and odd are empty, and unclassified is the entire array. We iterate through unclassified, moving its elements to the boundaries of the even and odd subarrays via swaps. Right. So subarray is a term that they're using for arrays that are in the same array. They're not separate arrays. So we iterate through unclassified, moving its elements to the boundaries of the even and odd subarrays via swaps, thereby expanding even and odd and shrinking unclassified, right? So they basically sort of group this into an unclassified set of numbers, and we're trying to shrink what we think of as unclassified. So I'm assuming, I mean, even before looking into this problem, let's try and sort of envision what that probably looks like, right? So it's probably like question mark, question mark, question mark, question mark, question mark, right? And so you go over to right. So you go into this and it says 2, and you've decided the first part of your subarray is supposed to be even, so you leave it there. But you see 5. You probably will switch 5 over with this question mark, and then check out what this question mark is. And then if it's 3, for example, swap it out, move it back here, and bring in the question mark, and then so on and so forth, right? That's my assumption, and let's see how that goes. However, you're required to solve it without allocating additional storage. Okay, initially, even and odd are empty, right? That makes sense, right? In our example, it was just question marks. Yeah, so they're pretty empty. Um, and unclassified is the entire array. Perfect. We iterate through unclassified, moving its elements to the boundaries of even and odd subarrays via swaps, thereby expanding even and odd, shrinking unclassified. So let's call, I'll work through the problem here. Um, so our function is called even odd, even do. Um, so you're gonna wanna check. Okay, so these are probably these are probably the pointers, right? You have your next even and your next odd. Okay, um, so those are the two pointers. They're both being initialized to 0. Oh wait, no, that's not how that works. Um, yeah, okay. So this is kind of weird Python syntax. I thought it was kind of strange at least. So what this is doing is basically setting next even to 0 and next odd to length of a minus 1. I don't think it's super readable, especially because, sorry, sidetracking here real quick, but let's say you have an array that's 1, 2, 3, 4, right? And if you wanted to swap elements in this array, let's say you wanted to swap 1 with 3, the position of 1 and 3, you can do that by doing a of 0, a of 2 is equal to a of 2, comma, a of 0, right? And then now I type in a and I've got that swap, right? So this looks a lot like that syntax, and that's why I'm not a huge fan of it. So I'd probably write this as two separate lines. But yeah, I mean it works like it works. Just to make sure, let's just run this line, right? Just to make sure that it actually works how we expect it to, or at least how I expect it to, right? So next even should be 0, and next odd should be, I think, 3, right? Yep. Okay. All right. Cool. So we're okay. So okay. So we've got our initial variables. Um, while next even in this case is less than next odd. I'm just gonna work through this and then we'll try and get it. So why is it next even, next odd? This is kind of weird. I don't know. I honestly don't know right now. We'll get there. If a of next even mod 2, right? So the modulus operator basically will check for the remainder of an operation. So if you think of divided by 2, you'd get how many times it could be divided by, but a modulus would give you the remainder. So if you were to do 5 mod 2, you'd get 1, and that would mean it's odd. So that's a conditional check. This line is a conditional check for if it is an even number. Then you would move next even up by 1, right? So I would assume how this sort of works is you have an array. 1, 2, 3, 4, 5, or unclassified, right? But basically, how this would work is you start. Okay, it's while next even is less than next odd, right? And we have next even as 0, so that means that would start with. Let me switch these symbols around so that it's easier to work with. Yeah. So next even would be here, and next odd would be here, right? So I'm just gonna leave that little box there or whatever to help us start or help visualize things, right? I don't have a drawing pad. Um, so what that sort of does for you is, okay, while next even is less than next odd, you do this first conditional check and then plus 1, right? So let's run through the same array, right? If it's even, if it's even, increase next even, which it's not. So next even is, I'm just gonna, okay, the first error is next even, the second error is next odd, right? I don't want to put more variables and keep you tracking that. It's much easier if you just look at it. Okay, so that's, nothing's happening there. However, else, it's this condition that's kind of weird, right? Why not just while an entire array, like while, or for every element, or while every element, right? But I guess we'll find out. While a next even, comma a next odd is equal to a next odd, comma a next even. Um, next. Okay, all right. So this was the swap that I was talking about, right? So if you remember what I was saying, it's this syntax. Uh, Sorry if I say a lot or if I sidetrack a lot. Please feel free to skip around a bit. Um, but I'm trying to just throw in information that I think might be useful. I don't know, whatever. Um, so you have okay. So if it's even, this boy jumps up, right? But if it's odd, then you swap with next odd, right? Okay. So next odd, and then next odd comes down an index. All right. Okay. So Um, I wish I could ask someone to keep track of this. Okay, all right. So while let's run through this, right? So while next even is less than next odd, next even is less than next odd, clearly, right? Um, next even is less than next odd. Yeah, that's perfect. Okay. So if that's okay, so we go through it. Is it even? No. Else, which yeah. Then you swap these two numbers. So you swap 1 and 5. And this boy moves down a number. Whatever. Yeah. Okay, so now we do it again, right? Um, uh, Next even is less than next odd, so this moves over. No, is this odd? No. Is it even? No. Um, so else, and you swap it. So you have 4. I don't know if you guys can see this, but it's already working. I mean, obviously, this guys wrote a textbook about it. Uh, yeah, so that's true. And so we can move this over a bit. Okay, don't go away. Um, yeah, and so we run through this again. We say if A is A of next even is, and that is true, right? Our boy is even. So, yeah. And now our last iteration is, or I don't know if it's the last iteration, we'll find out. If A of next even mod 2 is equal to 0, which it's not, swap these two, right? So you'd have 5, 3. And swap it, and then, yeah, there you go. So now this condition is now broken, and we've got our array in the way that we want it to, right? So this condition, although it's kind of weird, is useful, right? I don't know if it's super intuitive, but it works, right? Like I'm trying to find a way how I could find like sort of remember that, right? They're saying if you have an array, you'd want to try and abuse the two ends of an array and see if it could be useful like that. But I don't know. This isn't super intuitive. Um. All right. Yeah, I think I'm just gonna leave it there. Right? It just, I mean, because it has to stop here, right? So it has to sort of do that. So, I mean, you, I'm saying, why not a for through all the elements? You'd have to stop here because otherwise it could continue, and then 3 and 2 it would compare, and if it's even, um, I think it'd be fine. But if it was odd again, oh wait, no, if it was even, no, if it was odd, it would be a much bigger problem because it would swap, right? 3 and 2 would swap, and then you'd essentially lose your array. So you'd need to stop it there. So I guess trying to remember it, I don't know. If you guys have a great way of remembering this, please put it out in the comments. Okay, all right. The additional space complexity is clearly big O of 1, right? Perfect, yeah, I mean, that makes sense. Um, a couple of variables that hold indices and a temporary variable for performing the swap. Yeah, that's true. Indices and a variable to hold the swap. Yeah, that's not really the case because Python's got this. Otherwise, it's nasty. I mean, yeah, there's a bunch of different ways to do it, but it's generally use a temporary variable, and that's what they're talking about. We do a constant amount of processing per entry, so the time complexity is big O of n. Yeah, that's true. Yes, we go through every entry in some way or form. So n is your number of elements in the array, and we go through all of them. So it's a big O of n operation in terms of processing and time complexity. Two different types of complexity are space and time, right? Array problems often have simple brute force solutions that use big O of n space, but there are subtler solutions that use the array itself to reduce space complexity to big O of 1. Yes, that's true. The base. Um, yeah, filling an array from the front is slow, so see if it's possible to write values from the back. Okay, that's the idea. Instead of deleting an entry which requires moving all the entries to its left, consider overwriting it. Dealing with integers encoded by an array, consider processing the digits from the back of the array. Alternatively, reverse the array so the least significant digit is the first entry. Be comfortable with writing code that operates on subarrays. Be comfortable with writing code that operates on subarrays. Okay, I mean, I would assume that's what this ordeal is. Uh, Instead of deleting an entry which requires moving all entries to its left, consider overwriting it. Okay, sure. Be comfortable with writing code that operates on subarrays. It's incredibly easy to make off by one errors when operating on arrays. Read past the last element of an array is a common error which has catastrophic consequences. Right here. If this was a less than or equal to, it wouldn't work, right? That's why I hate these things. Okay. It's incredibly easy to make off by one arrays when operating arrays. Reading past the last element of an array is a common error which is catastrophic consequences. Don't worry about preserving the integrity of the array, sortedness, keeping equal entries together, etc., unless it is time to return. That's actually a good point. I don't know. I've never seen that, but sure. An array can serve as a good data structure when you know the distribution of the elements in advance. For example, a Boolean array of length w is a good choice for presenting a subset of 0, 1, dot, 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 w minus 1, right? Okay, w minus 1. When using a Boolean array to represent a subset of 1, 2, 3, dot, 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 n, allocate an array of size n plus 1 to simplify indexing. When operating on 2D arrays, use parallel logic for rows and columns. Sometimes it's easier to simulate the specification than to analytically solve for the result. For example, rather than writing a formula for the ith entry in the spiral order for an n by n matrix, just compute the output from the beginning. Okay, alright, those are the top tips for arrays. What did that even last one mean? Sometimes it's easier to simulate the specification than to analytically solve for the result. Yeah, I agree. Yeah, I mean, that's kind of what we did, right? That's the only reason it even made sense. Use parallel logic for rows and columns. I'm not really too sure what that means, but I guess we'll find out eventually. Know your array libraries. Arrays in Python are provided by the list type. tuple. Uh, we've always been calling it the tuple. I think it's something to do with collections. Okay, I'm sorry. I'm blanking out right now, but I'll get back to you on that. Or not, and you can find out what it is on your own. The tuple type is very similar to the list type, with the constraint that it is immutable. Okay, it's got it right here. Goddamn. The key property of a list is that it is dynamically resized. An example that's what an immutable array or list is. Um, it's immutable in this, and it cannot be dynamically resized. There's no bound as to how many values can be added to it, in the same way values can be deleted and inserted at arbitrary locations. Know the syntax for instantiating a list. Example 35711 plus 0 times 10 list range. Okay, yeah, I mean, this is really important. List comprehension described later is also a powerful tool for instantiating arrays. The basic operations are length of a dot append. Okay, alright, so there's a bunch of pointers here. Check it out in your book. It's just really, really, really useful. I think I've read this ahead of time, so I'm gonna skip over it, but I would really recommend you don't do so. All right, so now moving into the beef of the problem, right? We're gonna be working on problem 5.1. All right. Yeah, cool. Let's do that. I've called it this because in PyCharm you can't start it with the 5.1, I think. Right, so the problem's called the Dutch national flag problem. Also, please use PyCharm. PyCharm is really awesome. It's really useful to get used to learning how to use a debugger and stepping through things rather than just using console.out or whatever it's called in Python. Um, or print, or printf. I just realized console.out is a JavaScript thing. The quicksort algorithm for... Wow, I got insecure about that real quick. The quicksort algorithm for sorting arrays proceeds recursively. It selects an element, the pivot, reorders the array to make all elements less than or equal to the pivot appear first, followed by all the elements greater than the pivot. The two subarrays are then sorted recursively. Implemented naively, quicksort has large runtimes and deep function called stacks on arrays with many duplicates because the subarrays may differ greatly in size. One solution is to reorder the array so that all elements less than the pivot appear first, followed by elements equal to the pivot, followed by elements greater than the pivot. This is known as Dutch flag partitioning because the Dutch national flag consists of 3 horizontal bands, each in a different color. Okay? Uh, so I think the idea of this is that the quicksort sucks. I mean, it's not, it doesn't suck. It's phenomenal, but it's implemented naively. Quicksort has large runtimes and a large call. Okay, and a deep function called stack on arrays with many duplicates. So a solution to that is to reorder the array probably before passing it in. So, or something of the sort. So with this particular algorithm probably is useful um, as a precursor to quick sorting. I just say these things because it's really, really hard for me to like learn something without it being useful or something that I can see being useful, right? So why would you want to ever sort arrays like in the form of a Dutch flag? They've given us a reason, right? So this book is pretty awesome like that. Um, all right, yeah. So as an example, assuming that black precedes white and white precedes gray, figure 5.1b is a valid partitioning for figure 5.1a. If gray precedes black and black precedes white, figure 5.1c is a valid partitioning for figure 5.1a. So they're talking about different ways of partitioning it, and that's fine. This is just straightforward. It's uh, basically the two different ways that are in the picture are if the medium is your null. I mean, no, forget it. I mean, this is too straightforward. I mean, just look at the flags. Um, And think about the partition step in quicksort. Okay, now write a program that takes an array A and an index I into A and rearranges the elements such that all elements less than A of I, the pivot, appear first, followed by elements equal to the pivot, followed by elements greater than the pivot. I'm going to read that again because I didn't get it. Write a program that takes an array A and an index I and rearranges the elements such that the elements less than A of I, elements less than A of I, appear first, followed by the elements equal to the pivot. Okay, so you'd have these, then you'd have A of I, then you'd have elements greater than A of I. I guess it's equal to in the middle, but you get the point. Okay, the problem is trivial to solve with big O of n additional space. Is it? Yeah, it makes sense. I mean, you just put it into a bunch of. So that's really important to remember. Big O of n does not just mean one extra array. It's big O of 2n, 3n, 5n, 50n, 70n. All of that turns back into big O of n. So they're saying if you have three of the same sized arrays, can you do this? And the answer is probably yeah, right? Like you can just literally iterate through all of them and then put them in separate arrays. But obviously, you have to do it as good as you can. So you want to do it. I'm assuming they're going to say with minimal space. Where n is the length of A, we form three lists, namely elements less than the pivot, elements equal to the pivot, and elements greater than the pivot. Consequently, we write these values into A. The time complexity is big O of n. We can avoid using big O of n additional space at the cost of increased time complexity as follows. Sure, so that's it. Rather than three arrays, we're going to try and use less than that, and it's going to increase our time complexity because there's probably more processing. In the first stage, we iterate through A starting from index 0, then index I. In each iteration, we seek an element smaller than the pivot. As soon as we find it, we move it to the subarray of smaller elements via an exchange. This moves all the elements less than the pivot to the start of the array. Okay, as soon as we find it, we move it to the subarray of smaller elements via an exchange. This moves all the elements less than the pivot to the start of the array. The second stage is similar to the first one. The difference between that we move elements greater than the pivot to the end of the array. All right. So you got this. Okay, so it wants red, white, and blue is equal to range 3. So that's 0, 1, 2. Def. Define Dutch flag partition. Pivot index. Pivot is equal to A pivot index. Okay, so our first pass. Okay, remember what they said. There's going to be 2 steps, right? Okay, I'm just going to write that in the comments. First stage is iterating through A, the array, starting from index 0, then index 1. And in each iteration, we seek an element smaller than the pivot. As soon as we find it, we move it to the subarray of smaller elements via an exchange. So we're going to exchange elements if to the small side of the array. I'm going to say small side into a subarray. First stage elements to the small side of the array by swapping exchanges. What does this even mean? Okay, no. First stage exchanges elements smaller than the pivot. Moves elements smaller than the pivot to the smaller side by exchange. Exchange. Okay, alright, yes. Okay, so that's there. Alright, so first pass. I'm gonna leave out these comments because I don't think they're super. Group elements smaller than the pivot. Yes, right. Uh, no, I don't want it. For I in range length of A, right? So that's all the indexes, all the indices of A. So if you had A as an array, range will start with 0 and then go on, right? Look for the smaller element. For J in range I plus comma length of A, if A of J is less than pivot. Okay, so this is literally that, right? It's okay. Oh man, no one's gonna be watching my older videos because they're so weird. I'm gonna redo it as quick as I can, right? Like the explanation part. Okay, so super quick. Let's go over all of this. For I in range length of A, right? So that iterates the entire array A. For J in range I plus 1 length of A, what these two do is they form an array that looks like this. 0, 0, 1, 0, 2, 0, 3, 0, 4, then 1, 2, 1, 3. Basically, they let you compare elements that you haven't seen together. So if you think of a die, it'll do 1, 2, it'll do 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, right? Because 2 and 3 hasn't been a combination before, right? That's what these two parts of the array do. If I of j is less than the pivot, then you swap it, right? So basically, it compares every possible combination and then swaps it if it's less than the pivot. Okay, so this is essentially just selection sort. Second pass. Second pass. Any of you guys watched Psychopaths? I think it's pretty pretty fun, pretty great actually. I'm just saying that right now. I think that show is super underrated. I'm watching Watchmen right now. Pretty good. Okay, so second pass. Group elements larger than the pivot. Group. See, these are the things that I feel like smart people just leave out for the rest of us. What the hell is group? Okay. Mm, Mover to the smaller side is obviously less semantically correct, but makes more sense. That's just a joke. For I in reversed. Okay, so we're delving into some weird shit now. Range, length, A. Yeah, so, okay. This doesn't seem super simple, but I promise you it is. If A of I is less than the pivot, yes. Break. Okay, So, what they're trying to do here is, okay, what they're trying to do right here is do the same thing, but from the back of the array. So it's probably going to be like run through the same thing, but then backwards. It's going to be an inverse of this, essentially. But if a of I is less than pivot, if your element is less than the pivot, don't do anything. Break will just break out of that particular part of the for loop, and it will go to the next part of the for loop, which is good. So you have no identical entries. So for j in reversed range I, if, okay, so it's the opposite, right? So this did I plus 1 length of A, right? Why is it I plus 1? It's because it's the index plus 1. The index is going to be 0 index, and you don't want that. You want it to be an actual number. So I plus 1. Yeah. And then plus that for the separate array. Whereas here, you're going to be starting with range, and range will give you a 0 automatically. So if, man, that's such a bad example, explanation. Um, I can show you maybe in a bit. Pivot, or, because I think I understand it. Maybe I don't. Let me get there after I'm done with this. A of j, A of j, A of I. Brick. Yes. Why is all this yellow? What? Why is that even important? Oh, okay. I think I know what the problem is. It's, yeah, we want all of this to move. Yeah, so that's basically it. That would give you a selection sort. If you can sort of think of it as a flag, right? Yeah, got that formatting. You would have sorted equal, whatever, reverse sorted. And yeah, so basically you would have that from these conditions. Here, here would be sorted equal, reverse sorted. I'm not super comfortable with the indices here, right? Just to make sure, let's open up the console. Just 'cause. So this kind of a nice. Can I clear the console to now? No, apparently I can't. Print. I think it's print. Comma J. Yeah. So that's what that does, right? And this, I probably want to get rid of the break parts, or do I? Yeah, let's put in an array that's pretty simple to understand. 2, 3, 4. That went away. Pivot isn't defined. Right. Okay, so I probably missed that line here anyway too. No, here it is. The pivot is 2. Alright. 3 2 3 1 3 0. Why isn't it doing 2 2? Because it's not less than 2. Yeah. Or 2 1. 2 1. Okay, cool. Yeah, so this works. So this essentially will do everything. This will do just the top half, and that essentially gives you that segment that you want. The additional space complexity is now bigger. Okay. I think this next part is an improvement over the previous part. Yeah. The additional space complexity is now big O of 1, but the time complexity is big O of n squared. I n over 2 and all the elements before I are greater than a of I. All elements after I are less than a of I. Intuitively, this approach has bad time complexity because um, okay, let me break this into 2 parts, and I'll continue this later.